Hi everyone, today I want to share with you what I was working on in the summer. Let's start with some background knowledge. So GPUs, they are important in training deep neural networks. Well, we all know that models include parameters to train, but deep neural networks, they include many parameters. For example, VGG16 network, it includes around 140 million parameters. Well, you can probably understand why the traditional CPU approach is not efficient enough. GPUs, unlike CPUs, they have hundreds of simpler cores, which makes them really good in training deep neural networks. But one GPU, well, it's not really enough. We know that GPU devices they have limited memory, and the growth of model size outcompetes the growth of the GPU memory. For example, recently there is a 1,000 layer deep neural network that required around 10 gigabyte memory to train. Well, it's a lot larger than typical GPU memory. Though a few types of GPU might be useful in training this kind of cases, we don't really want to limit the training process to a few types of GPUs. The solution is to split one model on several GPUs, and the required memory for each GPU is going to be smaller. Well, so the traditional approach to split one model on several GPUs is the learning-based approach. It means like you use reinforcement learning to adjust the placement plan in order to minimize the execution time for each training step. This process takes days, even weeks to train. What is more, it only works for the specific model on several specific GPU devices, meaning that if you switch to another computer, you have to redo the training process, which is going to be very time consuming. We, on the contrary, adopt a different approach. We generate relation graph of the model, including the estimated runtime of each layer, the communication time between GPUs. Then we use three different modified traditional approach to split the relation graph on different GPUs. Our way can be completed in a matter of minutes, which is way faster than to use reinforcement learning. But we risk having a higher execution time for each training step. So we need to make sure our result is within a certain range of the optimal result produced by the reinforcement learning method. Well, currently we have implemented our approach on TensorFlow and the results look pretty good. For example, in the Inception V3 model, we are able to complete the distribution within 1 minute and our final result is within the bound. I am currently working on the PyTorch implementations of our project. In the summer, I have completed automatic generation of the relation graphs and the testing for some part of our approach. Since TensorFlow and PyTorch have many differences, our previous algorithms need to be modified when applied to PyTorch platform. This process includes continuously updating our code to minimize computation deviations. I will continue to work on this project in the fall, and I believe that our project could make some real difference in the machine learning world.
In this graph, you can see it's a relation graph generated using the AlexNet model. The points are the layers and they are connected by directed edges. This line means like I ran the virtual scheduler for AlexNet using 1 GPU and I get the result 59. And this line I run the REU execution for the AlexNet using 1 GPU. It's 63. Well, it's not perfect, but you can see they are very much similar. This is from another dataset and using O6 model. The blue points are the virtual scheduler time, the red points are the REU execution time, and the virtual scheduler runtime is always within 1 to 1.3 of the REU execution time.